Hello everybody. Today I will be going over 2007 number 6, a non-calculator problem. Let f be the function given by f of x equals e to the negative x squared. Part A asks, write the first four non-zero terms and the general term of the Taylor series for f about x equals 0. The first thing we do is we notice that the Taylor series about x equals 0 is just a Maclaurin series. So we can use the Maclaurin series for e to the u, which is the sum from n equals 0 to infinity of u to the n over n factorial. Since our u in this case is actually negative x squared, we substitute negative x squared for u in the Maclaurin series formula, and we get that e to the negative x squared is approximated by the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over n factorial. In order to write the first four terms of the series, we simply plug in n equals 0 through 3 into this Maclaurin series sum, and we get e to the negative x squared is approximated by 1 minus x squared over 1 factorial plus x to the 4 over 2 factorial minus x to the 6 over 3 factorial. Since the question also asks for the general term, we write out negative 1 to the n times x to the 2n over n factorial. The point breakdown on this question is 1 point for writing any two of the four first non-zero terms of the Taylor series for e to the negative t squared, and the second point comes from writing the rest of the first four non-zero terms of e to the negative t squared. What this means essentially is you can still get partial credit even if you don't know the entire Taylor series polynomial. So you should be trying to write as many terms as you can, even if you don't know how to write the whole thing. The third point was for the general term. Part B. Use your answer to part A to find limit as x approaches 0 of 1 minus x squared minus f of x over x to the 4th. The first thing we do is we notice that our Maclaurin series for f of x has the terms 1 minus x squared very conveniently. So when we substitute f of x here in our limit for the Maclaurin series we derived in part A, we can consequently cancel out the 1 minus x squared with the 1 minus x squared to get 0. Doing so leaves us with limit as x approaches 0 of negative x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus the rest of the sequence over x to the 4th, which just becomes negative 1/2. Now, some of you may be asking, how do you know that this whole thing will just become negative 1/2? Well, we notice that the only term that actually matters is negative x to the 4th over 2 factorial in this limit, because the negative x to the 4th over 2 factorial will cancel out with the x to the 4th in the denominator to just become negative 1/2, while the other terms in the sequence with larger x degrees, such as x to the 6 over 3 factorial, will have an excess of x in the numerator, which just causes the limit as x approaches 0 of the term to become 0. We know that this pattern will continue for the rest of the terms as well, since x's degree in the numerator only increases as the number of terms in the sequence increases. Point breakdown for part B is just simply 1 point for the answer. Part C. Write the first four non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0. Use the first two terms of your answer to estimate the integral from 0 to 1/2 of e to the negative t squared dt. The first thing we do is we apply the fundamental theorem of calculus. Integral from 0 to x of e to the negative t squared dt is equal to the antiderivative of this function at x minus the antiderivative of this function at 0. Substituting the Maclaurin series that we know for e to the negative t squared into this integral, we get the integral from 0 to x of 1 minus t squared plus t to the 4 over 2 factorial minus t to the 6 over 3 factorial, and on and on and on. With these four terms, we can integrate term by term, and remember to apply our fundamental theorem of calculus so that we get x minus x cubed over 3 plus x to the 5th over 10 minus x to the 7 over 42 minus the same sequence with 0 instead of x, which we know will all just become 0. The next part of the question is to estimate the integral from 0 to 1/2 of e to the negative t squared dt. Well, the way we do this is we plug in x equals 1/2 into our series that we got for the integral from 0 to x of e to the negative t squared dt. Using the first two terms here, we get that when x is equal to 1/2, 1/2 minus 1/2 cubed over 3 is equal to 11 over 24. The 3 points in this problem are, once again, 1 for getting 2 out of the first 4 terms right, another 1 for getting the rest of the first 4 terms right, and the final point for a correct answer. Part D. Explain why the estimate found in Part C differs from the actual value of integral from 0 to 1/2 of e to the negative t squared by less than 1 over 200. The way we do this is we have to notice that our Maclaurin series for the integral of e to the negative t squared is alternating. Not only that, but it also is positive and decreases to 0 as the number of terms approaches infinity. Altogether, this means that we can apply the alternating series error to our Maclaurin series for the integral. And we know that the alternating series error works by telling us that the next term, after the last term that we used in our sum, is always going to be the error of our sum. So since our sum contained the first 2 terms of the sequence, we find the value of the third term at x equals 1/2 in order to give us our error. So we plug in 1/2 to x to the 5th over 10, and we get 1 over 320. The question was asking us to prove that the integral from 0 to 1/2 of e to the negative t squared dt approximation that we found in Part C was only off by less than 1 over 200. Using the alternating series error, we found that our error for the first 2 terms is at max 1 over 320, which is less than 1 over 200, which means that we have successfully completed the problem. Some useful practice problems if you're having trouble with Taylor polynomials are 2004, 2009, 2010, 2012, 2013, 2014, 2015, and 2016 number 6. Thanks for listening, and I hope now you know a bit more about Taylor polynomials.